Hi everyone, welcome back. This is your struggling CS student. Today let's solve another LeetCode problem of the day. Let's take a look at today's problem. Problem 1408, string matching in an array. Now given an array of string words, return all strings in words that is a substring of another word. You can return the answer in any order. A substring is a contiguous sequence of characters within a string. So let's take a look at some examples. So S is a substring of mass, and hero is a substring of superhero. Okay. Hero S is also a valid answer, so they're telling us that the order of the answer doesn't matter. So ET and code or substring of LeetCode must it okay, blue, green, blue, okay. No string of words is a substring of another word. Look at the constraints. The constraints is words.length, the static is 100, and each character, each word has 30 characters. All the strings in the words are unique. Okay. So S is a substring of mass, and hero is a substring of superhero. Okay. So because this is an easy problem and the words.length is only up to 100, this means that we can essentially use a brute force approach, and for each word we check against every other word, and that would result in us iterating through all possibilities, and from there I believe we should be able to essentially get the uh, answer, right? So as long as one of the words is a substring of another word, then we can just append it to the answer. But actually I believe there's an advanced solution to this simpler problem. For example, if let's say words.length is 10 to the power 5, and words of I.length cannot be too big as well, I believe. I'm not sure if there's a similar question that is like more that represents the advanced variant. I'll try to solve this in using the simpler solution first, and then we'll upsolve it using the advanced method, which is involves using a try instead of brute forcing. And then we'll see if there's any similar questions that requires us to um, use the try method, and maybe we can do it in the same video, right? So let's try the brute force method first. So how would that look like? So we would say n is equals to length words for I in range of n, and then for j in range of n, you can say if I is equals to j, continue, else we'll check if the words of I we can do a function here. So is substring of words of I, and let's say the words array, then we'll do answer dot append words of I. Then we can just return our answer here. Answer is equals to the empty list. Then we'll define the helper function that is substring of a word in words array. Right. So this means what? So for words array, wait, hold on a second. Oh, no, we're just comparing two words. What I'm doing. Oh, oops. Words of J. So in substring, this is, let's say word 1 and word 2, right? So is words 1, words of I a substring of words of J? If so, then we append words of I, so it's substring. Then we can just do some sort of like a two-pointer or sliding window algorithm, where let's use this as an example. Actually, I think there might be a helper function, but let's try not to use the helper function. So we mess like this, we have one pointer here and one pointer here. If they don't have a match, then we will advance the word 2. Let's say this is word 1, and then this is word 2, right? So word 2, if they don't match, then we advance word 2. If they match, then we advance both of them. If they match again, we advance both of them. And once we exhausted word 1, that means we found word 1 in word 2, and then we can return true. Else, if word 1 has not been exhausted, then we will return false. So that is the manual way of implementing a substring. So we can say I in range of length of word 2, right? And we say we need a pointer variable as well. So pointer is equal to 0, I guess. Word 1 pointer. Yeah, maybe that's a better word. Or word 1 index, maybe. Like so. That's not good practice. Word 1 index like this. Just to be consistent with camel casing and snake casing. So if word 2 of I is equals to maybe let's do this, word 1 of word 1 index is equals to word 2 of I, then index plus equals 1, word 1 index, right? Then here we can just say return word 1 index is greater than or equals to length of word 1. I think we should be good. We should be good. Okay. Oh, I see. So basically, if word 1 index is already greater than equals to the length of word 1, then we can just break immediately. Huh? What happened? Oh, there's a space here. I see. All right, what's wrong? BU. The output is BU. Oh, I see. Okay, okay. Uh, okay. I didn't handle a case where, let's say, how should I put it? Basically, I will match. Not this code is only checking not for substring, but instead for a subsequence, and that's not what we want. Essentially, when we encounter another variable here, sorry, another character here which is not in BU, then we should return false immediately in this case, right? So we can say something like, we can just do a check here. If word one of index is greater than 0 and they are not equal, then we will have to return false, right? At this point. You can just break here, I guess. Okay, now what's wrong with this? ET. Oh, right, that makes sense. Now we have to scan it like this. Oh my days. Am I overthinking this? I think I am. I think I am. Yep, I'm definitely overthinking this. All right, this is my mistake. Basically, what we can do instead is we can maintain a sliding window of length 2, and we just need to check if word 1 matches the sliding window. If it does, then we can just return true immediately. Else, once we exhaust the sliding window, then we can return false. I think that would be a better implementation than this. So what we can do is sliding window length. That will be length of word 1. Then we would say we can build the window first. So window is equals to, should we do this? I guess it's fine since the characters, the number of characters are not too big. Is to the is what I mean to say is each word can only have up to a length of 30. So I guess we still can do this. Up to sliding window dot length inclusive. Okay, yeah, this is fine. So this is our window. Oh, wait a second. Then we have to remove the character from the left. remove the character from the left, and I guess we can track the count instead. We can track the count instead. We have to remove the character from the left and then append the character on the right. But what if they are in different order? What if they are in different order? Oh, unless we keep getting the string again and again. Oh, this is becoming a little bit hairy, I guess. Well, the cheat code way will be like this. I think that this helper function works or not. Okay, there's no such helper function. Ah, oh god damn it. I guess we gotta do it the old-fashioned way. So the old-fashioned way. Oh, that is a little bit hairy. Yeah, that is a little bit hairy. Well, let's try. For I in range of starting window.length to length of word 2. We gotta check if the initial window already matches. So, and this is not S, this is word 2. So if if word 1 is already equals to the window, we can return true. Else we have to do this check, and it's a bit hairy because what we can do is just this. We just build the window again. So for I to I plus this. Then we say if we do this check again, return true, else we return false. Oh, okay, what is wrong now? Wait, what? Why did it fail? Let's see this case. Let's print the window. S and SS. We're sure away here already. Let's print the window then. Print the window. Did I build the window wrongly? Length of word 1. Word 1, word 2, and then the window. Word 1, word 2, and then the window. Window looks correct. It looks like an off by 1 error because it's MA first, right? And now the window, it should be AS print I window. Index 2, 0, 1. Okay, yeah, it's off by a 1 error, but all right, what's the time and space complexity of this? And let's try to upsolve this. Honestly, this has taken too much time. It should have been way easier, but anyways, let's analyze the time and space complexity. So definitely there's an n square loop here, and this n square loop is up to the size of words.length, which is 100 in this case. So 100 times 100 times 30 probably. Yeah, 100 times 100 times 30, because this is substring, actually also takes up to words of j time, because we're always checking if words of I is a substring of words of j. And how we're doing that is, well, we are iterating through the what's that? We're iterating through words 2, meaning a sliding window, and then we're checking the substring. Actually, then we're recreating this window all the time. So that's actually words 1 times words 2. Oof, words 1 times words 2. So it's 100 times 100 times 30 times 30, which is not the best. So if let's say this is if words let words dot length be n and words of I dot length be m, then it's n squared times m squared, I believe. But let's give it a submit. Don't think this is the best solution unless there is a way for us to reduce this check, right? If we can reduce this check. Is there a way for us to optimize this part especially, right? Basically, it's all about adding one character to the right and removing one character from the left. Initially, I thought of using like a dictionary to just count the what's that? Count the number of characters, but if the order of characters is different, then you will get a wrong answer, right? Even though they have the same number of characters. Then I thought about using a queue. Now, using a queue, you still have to perform string comparisons. But maybe using a queue is better. Yeah, because this comparison itself is already taking up to O(n) time. And then we're building a window which also takes up to O(n) time. So maybe not. Maybe it's the same. Yeah, let's give it a submit. Oh no, wrong answer. That's bad. Okay. What's wrong? Ah, I see. Okay. I see. In that case, we can use a set instead. Return list of answer. A lot of careless mistakes for this one. This is horrible. Oh my days. Wait, what? Wait, why is this failing? Huh. Let's print words of I and words of J. And then we can print this as well. Okay, definitely our substring function is failing. Search and researcher is false. Okay. Let's do search and researcher. Let's see the window. Print the window here. And then we can print the window here. We need to print word 1 and 2. Search and researcher. Okay, this oh, this is confusing actually. Let's do this instead. The window, so word 1, no, this one, okay, word 1 and word 2. So we check like this. Starting at index I, so I plus the starting window dot length. Up to we are not including this index. Oh, no way. Yeah. Wait, why is this so off? This is our window. Our window is shrinking. What the hell is going on? Sliding window dot length, staying of word 1. Isn't that correct? 511. 713. 9 and 15. Starting window dot length is the length of word 1 is 0, 1, 2, 3, 4, 5. So up to 5, but yeah, I thought we wanted to start from this. Up to but not including. Should work though. Why is that? let me see starting from index 6. Index 6. Oh, I'm going to start from this. This is up to 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. Oh my god, okay, so it should be like this. It should be like this, which means what? Which means 1, 2, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5. This is the right and this is the left. So it should be up to I and I minus starting window dot length up to I plus 1 inclusive. Then now we can print this. Oof, a lot of careless mistakes for this one, which is horrible because that's bad for interview. This is really bad actually. But it's okay. It's okay. Okay, let's take a look again. 0 to 7. Maybe I should just do inclusive bounds so that it's a little bit easier to debug. 0, 1, 2, 3, 4, 5, 6. The window looks a little bit off. So I is index 6. So 0, 1, 2, 3, 4, 5, 6. So from here, it's up to I plus 1. Yeah, so to I plus 1. And then we want what? We want I minus sliding window plus 1. Yeah, okay. Oh, that was horrible. Quick submit. Okay, it's accepted. 12-day streak. Analyze time complexity. N square times M. Okay, yeah, about there. Alright, so is there a way that we can do better than this? Of course, the advanced way that I was thinking about, which could be overkill, right? Which could be overkill, but maybe that would have been simpler, is to use a try data structure where you can do prefix matching, or when you're searching a substring of a word and another word, essentially. So let's try to solve this after my horrible performance on an easy question where we're supposed to brute force this. But yeah, let's just do this for practice. That's it. Okay, so how does a try work? I guess I can sort of explain that quickly. So a try, essentially, let's say you're given, let's just an example here, right? Let's say is mass, and then you have S, hero, and superhero. Superhero. So in essence, what a try data structure allows you to do is you can, how should I say? A try is a tree of hash maps, right? Where the links between nodes represents the relationship, or the links themselves represent data, right? So let's just walk through one example. So initially you have a tree, you have a root node like this, and suppose you want to insert the word mass into your try data structure, right? So initially the root is null. I'll denote this as R maybe. Okay, let's just put it like this. Let's not go here. Okay, I'm just gonna represent the empty node as the root node. So initially when we are inserting, we can just say, maybe let's order this a little bit. So M here, you have a key and it points to another node. And then you have another key here that points to another node. Then you have another. So yeah, okay, my explanation is horrible, but basically, at this node, you'll maintain a dictionary, right? You maintain a dictionary or a hash map that maps the character as the key to another node. This is what I mean by using the links themselves to represent the data, right? And then now, let's say you want to check if AS is a prefix in your try data structure. What you do is you'll walk through your uh will substring match be easy to find in this case? Let me think about it. Maybe not. Maybe not because what? Because it's only for prefix, right? For prefix matching, a try data structure would be very good for prefix matching. But for substring search, okay, I think if you use advanced, maybe not a try, yeah, maybe not a try, I'm sorry, not a try. For prefix matching, yes, you can use a try, but this is a substring search. That means you need to use even more advanced tools that I have personally not learned of yet. But string searching algorithms is like, I think KMP string searching algorithm. There are others. So let's say KMP string search, string matching algorithm. There are also other algorithms, but KMP is one of them. Yeah, I think you will need to learn these in order to do the string search. Yeah, string matching, array string. Yeah, it's not a try question. It's not a try question at all. Yeah, okay, brute force to find one string of another or use the KMP algorithm. The KMP will definitely give you the most optimal. Not a try, because try is only for prefix matching. So I made a mistake there. Brute force, which is the one we did, for current word index, if they're equal, continue. Then we say if the words of current index, then we add. Oh, is that how you check if one word is in another? Let's see. Maybe I can learn something. Learn a thing or two. So you're telling me that instead of doing this, I can just return word one in word two. Okay, fine. Oh my God. Okay. Yeah, usually if you can use okay, and then I need to go and learn what this list comparison or something like that, or like checking if one list is inside of another list. Yeah, but if you can use built-in functions instead of doing it the old-fashioned way, usually it's a lot faster because Python can optimize the code. Okay, okay. Yeah, that's what I thought is m squared times n squared, not what LeetCode is suggesting, which is n squared times m. But what did they say here? Did they say the same thing here? N squared. Okay, so that's not very trustworthy. KMP algorithm. Oh my days. Please tell me there is a okay. Suffix try. Eh? There's actually a try solution. Okay, there's no KMP explore card, unfortunately. Suffix. Interesting. Suffix. Let's see how they do it. Insert the words, yeah. M squared times n. Still m squared times n, huh? Yeah, exactly. Okay, let me see how the try solution works. I'm not going to read about the KMP one because I myself don't know KMP. It's on my to-do list, but okay, let's see the try solution. So in this approach, users try to store all suffixes of any word in words. You then determine for each word if it appears as part of any of the suffix in the try. Okay, you need to try okay. So each try node represents a substring. The frequency that keeps track of how many times the substring represented by path has appeared as a suffix. And A map to storage. Yeah, okay. That's for each try node. Yeah. After defining our try class, we go over everywhere, insert it, each suffix of it into the try. Start from the root and check if the chart exists. If yes, incrementing frequency. Repeat the second character, and we repeat the second character. Repeat the same for the second character of the word. Otherwise, we create a new try node. Okay. After it installs all possible substrings as paths from the root node to the leaf node. The frequency count at each node reflects how many words in the array share the particular substring. Now determine which word we just iterate through all the characters traversing the try. When we reach the end of the word, we check the frequency of the word we are currently at. If it's greater than 1, it means the word is present as a substring of the word as well, not just itself, so we count it to the result. Okay, let's see how they do it. Oh my god, why is this so cancerous? Okay, track how many times this substring has appeared in the track. It maps the characters to their respective child node. For start index, self.insert word from the start index to the end. Oh, I see. That is nasty. That is nasty. Damn, okay. So essentially what they're saying is, if we go back to that same example that we had, let's say mass, right? So from the root node to a particular child node is M, A, S, there's one more, S. What they're doing is just storing all of it like this, storing all of it. So they're storing A, S, S, ha ha ha. Anyway, then we share S, S, and they're doing this. Okay, yeah, let's try that just for practice, right? And let's just try that for practice. So what we do is we do class of try nodes, dev underscore init, self, and then we have self dot. Okay, I'm not sure about the frequency part, but I definitely know you need the children. There's a dictionary, and conventionally you also have a flag, boolean flag to mark the end of a word. So class try, and dev underscore init, self. Self dot root is equals to no, it's equals to try node. Then dev insert word, right? Self of, let's say, word. So for C in word, and also in your current pointer, current equals to self dot root. If C not in current dot children, current dot children of C is equals to try node, then current is equals to current dot children of C. So that's the insertion. Then we need to check def prefix match self of word, current is equals to root, pretty much like this. For C in word, then we return true. We're just checking for prefix match, so if the link doesn't exist, we return false, right? So okay, now we have our try data structure set up. Let's initiate it. Not try node, but the try itself. And right, for word in words, should I call this root? Yeah, well, let's call this root. Maybe not, maybe the try. Try.insert of word. Okay, then for word in words again, we have our answer here. Rest is equals to this. Maybe a set. Yeah, maybe a set. So if try.prefix match of word, then rest.add word, and then we return the list of rest. Okay, this is horrible. Oh, right, because we can't just insert the word itself, we got to insert all suffixes of the word. So what does that mean? This means that for I in range of the length of word, try dot insert the word from I to the end. Okay, it's still very wrong. Why is that? For C in word, C now in current dot children return false, then we traverse down here, which is written true. Well, oh, so we forgot to mark the end. Current is equals to false. Okay, what's wrong? Self dot root. What's the output? Output is everything. Oh, the output is everything because I see. Okay. That's why they had to track the frequency. That's why they had to track the frequency. Basically, because now we have all possible suffixes of every word in our chart, then obviously every word is also gonna have a prefix match with all the all the uh, all the what? All the how should I put it? Well, all the words themselves. So what I mean by this is, let's use the same example, right? Now, once we have this data structure set up, maybe let's draw it a little bit nicer, as like this. Then, when we're asking if mass exists in our try data structure, the answer is yes, because, well, we store the original word here, right? Likewise, when we check any other word, like as for example, it also matches here. So that's why they had to track the frequency, because suppose you are you inserted this once, so all of this has a count of 1, right? And then you want to check if s is a prefix, right? But you would have also needed to insert s inside of your chart. So that would how that would look like is, initially when we insert mass, we also insert our suffixes, so this will be 1. Then you insert s, that will be a of 2, a2 like this, s2 like this. And not only that, because we're inserting all suffixes, so initially it will be as and then s itself. This means this would be 2. Okay? This would be 2. In fact, I just noticed a mistake here. This will not exist. In fact, that will be 3 itself. I see. That's why they had to track the frequency. And then you have to return if the frequency is greater than if the current dot frequency is greater than 1. It's greater than 1. Then now we have to track the frequency. So self dot frequency is equals to 0. Let's do 1 every time we create a triangle, right? Current dot frequency is greater than 1. Insert word. Then we create 1. Oh, yeah, maybe not. Maybe current dot frequency plus equals 1. Then we traverse. So this will be 0. Oh, hold on a second. Now we don't have any output at all. Okay, let's take a look. We create a child node that increment its frequency by 1, and then we traverse down to the children. Okay. Prefix match. Current dot frequency is greater than 1. What's current dot frequency? Is it always 0? 0, 1, 0, 0. Worked. C word. Huh. Calling out frequency is 19. 19? What the hell? Oh, okay. Wait a second. Maybe it's like this. Is it? Ah, okay. Oh, okay. I see. Yeah. That means we traverse to the child, then we increment the child, right? So, okay. So basically, if the relationship doesn't exist, the link doesn't exist. Okay. Say at this, let's just do a simple example as we insert mass. As we insert mass, this means that let's erase all this. Okay, we need to go from the top. As we so we check, hey, this is the empty root, and we're checking, hey, is M inside of our dictionary right now? Okay, because the empty root is not. We create a link here. This is represented by this code, right? We access the current node's dictionary, insert a key, create a try node, then we traverse to, so currently this is current, we traverse to the child, then we increment it by 1. So that would be, well, the frequency is 1 plus equals 1. Okay. Yeah, now it looks correct at least. So that's horrible handwriting. But f plus equals 1. Yeah, I hope that's a little bit easier to see. So what's the time and space complexity of this? Time and space complexity, this is, well, this is n times n, right? N times m, right? If we let n be the number of words in the words array, then this is n. And if we let n be the average number of characters in each word, then this is m, this is n times m. Now we are performing another operation here, which is also n. And then here, the prefix match. Wait, this is not n times m actually. Yeah, this is not n times m. This is n times m, but this itself takes up to m time as well. Takes up to m time as well because we have to create the suffix. And if we create a suffix, let's say mass, so the entire suffix, then the next character, next suffix, and so on. This is 4 plus 3 plus 2 plus 1. And if you recall your studies, this is actually the arithmetic progression. Arithmetic progression, which is basically O n squared. Yeah, it's basically O n squared. Decays to O n squared. So in this case, for our time complexity analysis, this is n times m squared. What about this loop? This takes O n time, and this perfect match actually takes up to the length of the word, which is n times m. So it's dominated by this, which is n times m squared. Let's just give a quick submit. Hopefully I didn't make any mistakes. I didn't. It's actually not faster than using the brute force approach where I use the built-in methods. But let's see if our time complexity analysis is correct. So if let's say n be the size of words and m be the length of the longer string, okay, fine. Then it's n times m squared, just like I said. Insert word and the insert string will involve I look to take O m time, insert string in the trees, and therefore let's see what they do. Okay, this is this part, and this is this part, okay? Yeah, 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 okay. Okay, yeah. Basically what I said. Uh, this has been a long one, even though it's an easy question. I thought this would have been much faster, but it is what it is. Just show the code again on the right side here, like so. And that's it for me. Happy grinding and have a nice day ahead. Goodbye.